Okay, so we have a presentation as usual, as you know. Yesterday we were dealing with the sampling design. Today we are going to deal with a very important topic, statistical tools used in data analysis. So we collect the data from a sample and then we analyze the data. That is what we are going to see. There are so many statistical tools. We will be dealing with a few which are most commonly used for primary data collection. Because you have to attend as many classes as possible to understand the different dimensions of data analysis and also according to your requirements. The data analysis tools for primary data analysis is different from the tools used for secondary data analysis, time series analysis, complex analysis. So there are so many analysis types. So today we are just introducing the most important, commonly used. Everybody uses these tools for primary data analysis. So let us look into that. I will switch off my video and then I will go to the presentation. Yes, so statistical tools in research. What you see in the background is the University of Kerala and the Maharaja statue is in front. The Maharaja who started the university in 1937. So this is the main campus, main university building built by the British people. Statistical tools in research. So we are going to understand some of the commonly used statistical tools in research. Okay. So first let us see as I said, there are so many statistical tools. Broadly, the statistical tools are classified into 4 groups. Let us see the classification. Statistical tools are used for different purposes. As I said, for primary data analysis, secondary data analysis, time series analysis. So they are used for different purposes. According to your purpose, you have to choose the statistical tool that is required. First category of statistical tools, they are called descriptive statistics, describing the features and characteristics of data. We have collected data and we are starting to analyze the data. So first we try to understand what are the features of the data, general features, characteristics of the data. Then we move on to the analysis. This is not an analysis, this is only a description. Analysis starts after that. Okay. Second category group of statistical tools are called inferential statistics. There in bracket, it is given at the end in bracket. Inferential statistics. Inferential statistics. That is inferring, estimating population parameters from sample statistics. So those who have attended yesterday's class will immediately understand this. We do not study the population, but we want to know the values of the population. For that purpose, we select a small sample, study the sample, calculate the values of the sample, and from these calculated values of the sample, we estimate the population values. That is called statistical inference. So the tools used for this purpose is known as inferential statistics. Third category of statistical tools are dealing with the complex relationships. So when you collect the data, there are so many variables and between the variables, there may be complex relationships. In that case, we may have to use a group of statistical tools called multivariate analysis. We are analyzing multiple variables and their complex interrelationships. They are called multivariate analysis. Then, supposing you are analyzing secondary data, measuring the growth rates of, say, time series data and projecting the future trends of time series data. This time series analysis is a very complex analysis, and for that we use econometric analysis. Econometric tools are used nowadays. Some 20 years back, there were no such analysis were common. The tools were there, but they were not commonly used. Now, because of softwares are available, econometric tools are also being used for analyzing time series data. So today we are going to concentrate on the first two, descriptive statistics and inferential statistics, which are used in all analysis, primary data analysis. All kinds of primary data analysis, we will require both the descriptive statistics and inferential statistics. If it is secondary data, we use econometric tools, so that is totally different. And then multivariate analysis is the next step from inferential statistics. So today we are going to deal with the first two. You may be familiar with some of these tools. So when I explain, so try to understand the point which I am explaining. You may be familiar with the tools, you may be familiar with the names of the tools, but you may not really know what the tool is doing, what it is really doing, how to interpret. Because now calculations are not required. Calculations are done by the software. So what you have to know, only two things. One, what is this tool used for? Or what is the purpose of the tool? Secondly, the software will give you the results. Then how do you interpret the results? You should understand. You should be able to interpret the results. That is the very important point. That is what you should really understand. Nowadays, calculation is not required. When we were doing research, we had to do the calculations because softwares were not available at that time. Only Excel was available. Then that is the situation now. Okay, so even if you know some of the things, but try to understand the point which I am explaining. So we start with descriptive statistics. This is not an analysis actually, it is a description of the data that we have collected. For example, let me give you an example. Suppose in a class, there are 50 students and the teacher conducts a test paper for maximum of 100 marks. The total maximum is 100 marks. 50 students are there. They are writing the test paper and they get marks. Naturally, the marks of the students will not be the same. The marks will be different, varying from 0 to 100. It will be different. Sometimes it will be all close to 50, 60. Sometimes it will be highly varying from 5 to 95. Sometimes most of the students will be getting above 70. A few will be getting below 10. Or sometimes the other way around. Most of the students will be getting less than 30. A few students will be getting 70 or 80. So you see, the distribution of the data will be different. So we have to understand, before we start the analysis, we have to understand the distribution of the data, the characteristics of the data. What is the status, academic status of the class? See, we want to know what is the academic status of the class. Because we have collected the marks of the class as a whole. We are not interested in one student or two students. The teacher may be interested. That is different. Here, when we have the data of 50 students, we are interested in what is the academic status of the class. Is it low? Is it good? Is it average? And is it dispersed? Or all the students having the same academic status? See, so many things we have to understand. So for that, we have to understand the features of the data, the distribution of the data, and we can calculate some statistical measures to understand the features of the data. That is called descriptive statistics. Quantity is calculated from the data set to describe different characteristics of the data. See, what is the central value? What is the variation in the marks among students? Is the marks symmetrical, equally distributed among the students? And what is the peakedness? Are the some students having very high marks, some students having very low marks, or are they all having an average kind of marks? So all these things we have to understand. So these are the four features we are trying to understand. And for that, we will calculate some statistical values. Measures of central tendency. We want to know as a whole, what is the status of the class? That is the central tendency. For that, we have three measures. These are all familiar to you in your school days itself. You would have understood, you would have studied how to calculate mean, median, mode. It's the average. In other words, it is the average, mean, median, mode. Mean is the average calculated by totaling and dividing by the number of items. Median is arranging the data in a serial order from lowest to the highest and taking the middle one, that is median. Mode is the most repeated mark. Say, supposing 45 is the mark which is obtained by 7 or 8 students, then we say mode is 45. So you get an idea about the central value. Then what is the variation? See, I told you all the students will not have the same marks. Variation is there. So what is the maximum marks? What is the minimum marks? What is the range between the minimum and the maximum? That shows the variation. Another method, another statistical tool used is quartiles, 25%. First quartile, second quartile, third quartile, 3 quartiles are there. First quartile, 25% of the students has less than that first quartile. Second quartile, 50% of the students have less than the second quartile mark. Third quartile, 75% of the students will have less than the third quartile mark. Say, for example, third quartile is 70. So 75% of the students will have marks less than 70. 25% of the students will have marks above 70. That is the third quartile. Then what is the interquartile range? What is the difference between the third quartile and the first quartile? Similarly, percentiles are not very commonly used, but quartiles are used. Interquartile range can be used, but the most common measure of variation is standard deviation. I am sure all of you will be familiar with that. Standard deviation. The square of the standard deviation is variance, or the square root of variance is standard deviation. That is calculated. There are formulas for that. So standard deviation expresses the variation. If the standard deviation is low, that means the variation of marks among the students is low. If the standard deviation is high, it shows that the variation of marks among the students is higher. Supposing all the students are getting, say, 35 marks. All the 50 students are getting 35 marks. There is no variation. Standard deviation will be 0. See, standard deviation will be 0. There is no variation. Supposing they are getting in between 35 and 45. Standard deviation will be very low. Supposing they are getting between 5 and 95, standard deviation will be high. This is what is meant by standard deviation. So the mean plus or minus 2 standard deviation will cover 95% of the observations. So 95% of the observations will be covered by mean plus or minus 2 standard deviation. Okay, so now measures of symmetry, the third characteristic that we want to understand, how are the data distributed? There is variation. So we have seen the central value, we have seen the variation, extended variation, but how is the variation? Is the variation symmetrical? Balanced? Is the variation balanced on both sides? Is the variation balanced on both sides of the mean? Is it symmetrical or is it asymmetrical? I'll show you a curve. Look at this curve. See, this curve is a symmetrical curve. This is called a bell curve. Supposing when you plot the marks of, this is the height of 14-year-old girls. The height of 14-year-old girls. The data is plotted on a graph. You get a bell-shaped curve. That means on both sides. That is, the mean is, the mean there, you can read the mean. Mean is 1.512. Standard deviation is 0.0741. So mean is 1.512. That is the, see here. Mean, you can see here. I'll show you. See, mean is 1.5. So this is the mean. The peak is the mean. So on this side, these are the girls with lesser than, height lesser than the mean. These are the girls with height more than the mean. Both are equal, both sides. So there are equal number of girls with less than the mean marks, and there are equal number of girls with higher than the mean marks. So the distribution, the variation distribution is symmetrical. It need not be always the case. Sometimes there will be more girls with less than the mean height, or sometimes there will be more girls with more than the mean height. So this curve will not be symmetrical. It will have a longer tail here. If there are more girls with lesser height, this curve will be, this will be a longer curve. Supposing there are more girls with higher than the mean height, this curve will be a longer curve. So this is what is meant by symmetry or asymmetry. Okay. So symmetry is measured by skewness. It is calculated. That's the formula. And 0 value represents symmetry. When you calculate skewness, if you get 0, that means it is like the bell-shaped curve which I showed you. The values are symmetrical. Then if you get a positive value, skewness is positive, that means right skewed, on the right side. There are more people on the right side. If you get a negative value for skewness, it implies the left skewed distribution. That means there are more people on the left side. So the curve will be more on the left side. Then look at this. Look at the height of the curves here. See, this is a normal. So sometimes you may have the height may be much higher. So this mean may be much higher somewhere here, or it may be somewhere here. So the height of the mean, the height of the curve. See, the height of the curve may be less than this or more than this. This is normal, middle. So it may be more. That means the curve is very high, peak. So the peak is more, or it may be flat. So this height may be here. So that means the distribution. So there will be more people with the higher height, and if the peak is here, if it is flat, that means the girls are having, all of them are having more or less the equal height, equal to the mean. That is called, the height is called peakedness. The height of the curve is called peakedness or flatness, whether that curve is high or flat. It is measured by another measure called kurtosis. Again, there is a formula for that. It can be calculated. The software will do the calculation. You will get a value. The absolute kurtosis for normal distribution. Normal distribution, the one which I showed you in the curve. There is a normal distribution. So if it is a normal distribution, when you calculate the kurtosis, you will get a value of 3. Relative kurtosis is absolute value, which you get minus 3 is the relative value, but absolute value is enough. So 3 is the normal value. If you get a positive value, if you calculate relative value, means absolute value minus 3. If it is positive, it indicates a peaked curve. If you get a negative value, it indicates a flat curve. When you draw it, you can see, you can understand. Even without calculating, you draw the diagram, plot the figures on the diagram, immediately you can understand whether it is a peaked curve or a flat curve. So all these things describe. So these 4 things, we have now seen 4 things. One is the mean, then the variation measured by standard deviation, then symmetry measured by skewness, and the peakedness or flatness of the curve measured by kurtosis. All this is very good. So you will get a general idea about how the data are distributed, nothing more. It is just descriptive statistics. It is not an analysis. We are just describing the features of the data. After that, the analysis starts. So analysis starts with inferential statistics. Inferential statistics. So in any study, primary data, you take any study, first there will be descriptive statistics. In the analysis, they will show you the descriptive statistics will be calculated and shown. Then we move on to inferential statistics. That is the real statistics. Now we are going to understand what these inferential statistics are. So it is concerned with making inferences from samples about population. Yesterday's class, we have seen that. I was emphasizing that point several times. So we are collecting the sample, collecting the data, calculating the sample values, and from there we are estimating the population parameters. For that we use inferential statistics. For example, if you find a relation between 2 variables, supposing you find an association between 2 variables, we would like to know whether it is a real association existing in the population or whether it is a chance association existing only in the sample. So it may be a chance association existing only in the sample, or it may be a real association existing in the population. So we want to know that. For that, we use what is called inferential statistics. If you find a difference between two samples, see, when we are studying, in all of our studies, we are collecting data from respondents, people. So all the studies, so the sample comprises of respondents, and the respondents are, so in the respondents, there are different groups of people. There will be male and female respondents. There will be young and old or middle-aged respondents. There will be people with low income and high income. There will be people residing in rural areas, urban areas. So you see, there are different types of people among the respondents, different types of groups. So the sample will be divided into different groups. Your study sample comprises of different types of people, so that we divide the sample into different groups based on demographic variables. Your sample will be divided into different groups based on demographic variable, and we will study the difference between male and female. So you get the value for male and female. Is there a difference in the values of male and female? Take the example which I gave you before. In the class, there are 50 students. Say 20 of them are boys and 30 of them are girls. 20 are boys, 30 are girls. So we are interested in knowing whether the marks of the girls are higher than the marks of the boys, or whether the marks of the boys are higher than the marks of the girls, or are they different, or are they the same? Very interesting question. Very interesting question. Something we should know, and then try to find out why. Supposing there is a difference, then the analysis starts. Why there is a difference? How it can be corrected? So this is how research goes. Research tries to find out a fact, difference, whether the difference is existing. Then, why the difference is existing, how it can be corrected. That is your outcome of the research. This is how research goes. Supposing there are rural students and urban students. Rural students and urban students, they are getting marks. Is there a difference in their marks? See, so we want to find whether there's a difference between two samples or groups. And we would like to know whether this difference exists in the population, not in the sample which you have selected. That is a chance difference. Is it a real difference existing in the population? So, in most of the primary data analysis, we will be dealing with the relationships between variables. In our study, there are so many variables, and these variables are interrelated. So we will be interested in studying the relationship between the variables. That is one part of the study. The second part of the study, in our sample, in our respondents, there are different groups. So are there differences between the groups? Very interesting question. That also we have to find out. So these are the two types of analysis commonly found in research. And for this is used for hypothesis testing. Hypothesis testing. We will say there is no difference between the two groups. Null hypothesis. There is a difference between the two groups. Alternate hypothesis. There is no association between the variables. Null hypothesis. There is an association between the variables. Alternate hypothesis. And how do you test the hypothesis? We have to use inferential statistics. So this is data analysis, the starting point of data analysis, most commonly used data analysis or hypothesis testing. This is what we are going to study. Okay. So types of inferential statistical tools. So we have already seen there are two types now. One is dealing with the study of association between variables. There are so many variables in our study. We are dealing with so many variables. So is there an association between the variables? The theory will be saying that there is an association between the variables. So we want to test actually whether that association exists in reality. A second type is, we have seen just now, we have seen the tools used for the study of differences between groups. So these are the two inferential statistical tools. Study of association, study of differences between groups. Okay. So we move on to association between variables. How do you study the association between variables? Okay. Two tools are used for studying the association between, as I said, most of these things you may know, but what I am highlighting is something else. You may have studied about what is regression, what is correlation, but in research, that is not what is interesting. In research, something else is interesting. That statistical inference is what is important here. Okay. So two statistical tools used: correlation and regression. Correlation is not very important. Regression is a continuation of correlation, that is more important. Correlation, it studies the association between variables that may be related. If two variables are related, we can find out whether they are related by finding out the correlation between the two variables. What does this correlation measure? It's a measure of covariation. It is not a measure of causation. It does not measure, say for example, I'm going to give you an example, advertisement and sales. Advertisement and sales. They may be related, advertisement and sales. But that does not mean that advertisement is causing the sales. It is not a study of causation. Correlation does not measure causation. It only says that is covariation. When advertisement increases, sales also increases. Though there is a covariation. There is a variation in advertisement and there is a variation in sales. That is a covariation. When there is a variation in advertisement, there is a variation in sales also. So we call it a covariation. What is the reason for that variation? That is something else. That is something else. So for example, there may be a variation between people who are smoking and people who are having lung cancer. People who are smoking and people who are having lung cancer. So when the people who are having who are smoking increases, the people who are having uh, lung cancer also increases. So you find people who are smoking, they are also having lung cancer. So both people who are smoking, they are having lung cancer. Correlation, if you find out, if you calculate correlation, you will find a correlation. But that does not mean that smoking is causing lung cancer. That the medical science will have to find out. We cannot find out. Statistician cannot find out. Medical science will have to find out whether lung cancer is caused by smoking, whether smoking is causing the lung cancer. We can only find out, we can only say that there is covariation. Is it because of smoking that lung cancer occurs? That the medical science will find out by other tests. So understand, again, there's a misunderstanding. Many people confuse correlation as a study of causation. No, it is a measure of covariation. It indicates the magnitude and direction of covariation. If both are increasing, we say it is positive correlation. If one is increasing, the other is decreasing, we say it is negative correlation. You must be familiar with all that. It also shows the magnitude. How much is the covariation? It may be very little, it may be very high. I'll show you the values. Statistical measure of correlation. Pearson's coefficient of correlation, R. So correlation is measured by R. There's a formula for that. It may be positive or negative. The value that you get for R may be positive or negative. Positive means both the variables are moving in the same direction. If R value is negative, one variable is increasing, the other variable is decreasing. For example, when price of a commodity increases, the demand will decrease. When price of a commodity increases, naturally the demand will decrease. So you will get, when you calculate correlation, you will get negative correlation. Okay. See, it varies from -1 to +1. -1 to +1. 1 means very high correlation. 0 means no correlation. 0.2 means small correlation. 0.5 means medium correlation. 0.8 means fairly high correlation. So it varies from -1 to 1. Now, the square of the correlation is called coefficient of determination. That is a very important measure, coefficient of determination. R square, the square of correlation, is called coefficient of determination. It measures the extent of variation explained by the relationship. How much of that variation is because or is happening together? How much of the covariation in the, for example, sales and advertisement. Sales and advertisement, you find out correlation. Supposing you get 0.6 as correlation. Sales and advertisement, correlation is 0.6. Square of correlation, 0.6 into 0.6, 0.36. 0.6 into 0.6 is 0.36. It can be converted into percentage. R square is converted into percentage. 36 percentage. 36 percentage. That means it measures the extent of variation explained by the relation. That means, see, both are increasing. Sales is increasing, advertisement is increasing. So 36% of the variation in sales. So when sales increases, advertisement also increases. But how much is the covariation there? Only 36%. So 36% of the covariation of the variation in sales and advertisement are covariation. The balance, 64% of the increase in sales is covariated with some other variables. Some other variables we do not know. So that is all. So it's an important measure R square. Okay, these things I'm leaving out because we don't have much time. Now the question, is correlation significant? In statistics, when you're studying statistics and correlation, you calculate correlation R square, that is enough, finished. Your question is over. In the examination only that is asked. But when you are doing research, you calculate the correlation, then comes a question, is this correlation significant? So this word significant, if you refer to the dictionary, you will find significant means important. English dictionary, you will find significant means important. Here it is not, the meaning is not that. We are not asking whether correlation is important. Correlation is important, we know that. This question means something else. Is correlation significant means, is correlation applicable to the population? You have calculated the correlation of a sample. Is it applicable to the population? If it is applicable to the population, we say the correlation is significant. If it is not applicable to the population, we say the correlation is insignificant. This question you should understand first, the meaning of the question. So, if this correlation which you found in your sample, if it is applicable to the population, we say it is significant. So, how do you know whether it is applicable to the population? For that, we use inferential statistics. We use a statistical tool to find out whether this correlation that you found in your sample is applicable to the population. That is what we are going to see. In research, universe parameters are inferred from sample statistics. So I said in the previous case, sales and advertisement. You took a sample of sales and advertisement, you got a correlation of 0.6. 0.6. That is the sample correlation, sample statistics. What is the statistics or correlation of the population? If you take the sales and advertisement of the entire, all the companies working in a particular place or industry, we have just taken a sample. There is a correlation, 0.6. Fine, good. Is this correlation, is the population having the same correlation? What is the correlation of the population? That is what we want to know. Is it 0.6 or near to 0.6? We are estimating. So that is what we want to find out. Is it applicable to the population? When correlation is significant, the inference is that correlation exists in the population also. That is what I said. But how do you find out whether it is applicable to the population? For that, we use what is called p-value. P-value means probability value. P-value, probability value. It is written shortened as p-value. It indicates the probability of the correlation occurring by chance. The correlation might have occurred in your sample by chance. When you take another sample, it may not be there. So just by chance, the correlation has occurred. So p-value indicates the probability of correlation occurring by chance. So what is the probability of correlation occurring by chance? Probability value, say supposing probability value is 0.02. 0.2. 0.2. 0.2. That is 20%, in other words. So probability value is expressed in decimals equal to 0.2 is equal to 20%. So that means there is 20% chance that the 20% chance that the correlation exists by chance. What it means is, if you take 100 samples, we have taken one sample, we found out that it has a correlation. If you take 100 samples from the same population, if you take 100 samples, in 20 cases, 20%, 20 cases, this sample may not apply. 20, the p-value indicates the probability of correlation occurring by chance. In 80 cases, if you take 100 samples, in 80 cases, this probability will be there, but in 20 cases, this probability will not be applicable. So, the correlation that we are calculating, we have to know whether this correlation is applicable to the population. That means if we take more and more and more samples, will it be applicable? That is the question. We have taken only one sample. But we cannot go on taking more samples, but we want to know. We have taken one sample, we calculated the correlation, got 0.6. So we want to know if we take more and more and more samples, say if we take 100 samples, in how many samples this correlation of 0.6 will be there, in how many samples this correlation of 0.6 may not be there. So p-value indicates the probability that in how many cases it will not be there. So when the p-value is less, that means the chance of the correlation occurring by chance is less. That means it is a real correlation. See, if p-value is less than 0.05, this is our cutoff point. In social science, we use 5%, you know that. In social science, our cutoff is 5%. So if p-value is less than 0.05, that means 5%, correlation is stated to be significant. That means in 95 samples, this correlation will be there. If you take 100 samples, in 95 samples, this correlation will be there. In 5 samples, it may not be there. Doesn't matter. So we can say that this correlation is applicable to the population. So this concept you have to very clearly understand. We are taking a sample, finding out the correlation, and the software will give you the p-value also. And we look at the p-value, and based on the p-value, we decide whether this correlation is applicable to the population or not. For that, the p-value should be less than 0.05. If the p-value is less than 0.05, that means only there is this very, very small chance of this correlation being insignificant or not applicable to the population. It is in 95 cases, this correlation will be there. If you take 100 samples, in 95 samples, the correlation will be there. So we can say this correlation is applicable to the population and not only just to this sample. Okay, this is the key point. In all the rest of the presentation, this point will be coming up there. P-value being less than 0.05 or more than 0.05. Okay. This is correlation. Now, I told you correlation is not very important. We have to move on to regression analysis. Regression analysis. What is regression analysis? It's a continuation of correlation. It's a study of relationship. Study of relationship between different variables. So If you study the relationship between two variables, one variable will be categorized as dependent variable, and the other variable will be categorized as independent variable. In the case of sales and advertisement, sales is depending upon advertisement to some extent. So we can say sales is a dependent variable, advertisement is a independent variable. So for a dependent variable, there may be many independent variables. We may take just one important independent variable and let's try to understand what is regression analysis. Example, sales is the dependent variable, advertisement is one of the independent variables. Regression analysis, in correlation you get an R value. In regression analysis you get an equation showing the relationship between the two variables. It is an estimating equation. Two values will be calculated in the equation. Two values called alpha and beta. These are Greek letters, alpha and beta. So in the regression analysis, there will be two values calculated, alpha value and beta value. Beta is called regression coefficient. That is the real regression value. Regression coefficient. It measures, what does it measure? It measures the change in the dependent variable due to the influence of the independent variable. Due to the influence of the independent variable. For example, read again, once again, read it. Beta measures the change in the dependent variable, sales, due to the influence of the independent variable. Independent variable is the advertisement. So when advertisement increases by 1 rupee, sales will also increase by some amount. That amount is measured as beta. When an independent variable advertisement increases by 1 rupee, there will be a covariation. There will be a covariation. This is also a study of covariation. So there will be a variation in the sales to some extent. What is that? How much variation happens in sales? That is measured by beta. Alpha. Alpha shows the level of the dependent variable independent of the influence of the independent variable. Once again, read it. Alpha shows the level of the dependent variable, sales. What is the level of the sales? The dependent variable. Independent of the influence of the independent variable. Independent of the influence of advertisement. Even if there is no advertisement, there will be sales. Even if there is no advertisement, independent of the influence of advertisement, there will be sales. Some sales will be there. That sales is known as, that is measured by alpha. Okay. Example. Sales Y. The dependent variable is designated as Y. So supposing these are the sales values, X, the independent variable is represented by X, advertisement expenditure. These are the advertisement expenditure corresponding advertisement expenditure. This is the regression equation. Y is equal to alpha plus beta X. A plus B, alpha plus beta X. 1500 plus 100 is calculated. When you calculate, you will get 1500 plus 100x. So that means even if there is no advertisement, you will have 1500 rupees sales. That is alpha. Even if there is no advertisement, there will be 1500 sales. When you are advertising, what happens? When you advertise, when the advertisement increases by 1 rupee, sales will increase by 100 rupees. Beta. That is the increase in the dependent variable due to the influence of the independent variable. So when 1 rupee, 1 unit change occurs in advertisement, sales will increase by 100 rupees. So this is the meaning. So this is a much more important equation to study the relationship between the variables more than correlation. Correlation just says that there is a covariation, that's all. How much is the variation we do not measure in correlation. Here we are clearly measuring what is the sales without the advertisement, what is the influence of the independent variable, how much is the change, and so on. Very good. Now, this is this is the result we get from a software. When you do an analysis in the software, you will get a result. This is the format in which the result comes. Read the heading, regression analysis. Regression analysis. R square is already calculated, so you don't have to calculate correlation separately. When you do regression analysis in the software, R is there, 0.98, very high correlation. R square is 0.96, so both are calculated. Standard error, I'm not explaining all the terms. I'm only explaining what is required here. If it is a statistics class, of course, naturally we'll explain all that. N means number of items, sales and advertisement. 12 items were taken. This is another example which I did. K is 1. Independent variable is 1. Dependent variable sales. You can see on the top here, dependent variable sales. So on the top, all these are given. This is the regression output. Intercept, alpha is called intercept. Beta is advertisement, is the independent variable. So intercept means alpha. Alpha, intercept. Look here. How much is the intercept? See the coefficient. Read the coefficient here. 1964. 1964 alpha. 1964.50 alpha. You know what is alpha? Alpha is the sales which happens without any advertisement. Okay, fine. In the sample, there is sales without advertisement 1964. Is it applicable to the population? That is what we are interested in. We are not interested in the sample. You see, we are not interested in the sample. We are interested in the population. From the sample, we have to estimate whether it is applicable to the population and say whether it is significant, whether the regression alpha is significant. So our question is alpha significant? Look at p-value here, marked in yellowing. P-value, see, p-value 0.0001. So when do we say that it is applicable to the population or it is significant? When the p-value is less than 0.05. So it is much less than 0.05. So we say that this alpha 1964 is applicable to the population also. It is applicable to the population also. But what is the value of alpha in the population? The value of alpha in the sample is 1964. What is the value of alpha in the population? We have to estimate it between a lower limit and an upper limit. Between a lower limit and an upper limit. See here, 95% lower limit. We cannot get the exact value. We are only estimating. So estimation is between a lower limit and an upper limit. See here, 95% lower limit, 95% confidence. In 95% of the cases, the lower limit, the limit will be between 1297, see, 1297, and the upper limit is 2631. So out of 100 samples, in 95 cases, in the population, 95 cases, the value of alpha will be between, in this sample it is 1964, but in other samples it will be varying between 1297 to 2631. But in 5 samples, it will be beyond the lower limit and the upper limit. I hope it is clear to you. So try to understand. Okay, try to understand the result. That is what the result is given by the software. You don't have to do anything. All that you have to know is you have to understand it, interpret it. Okay, so if you take 100 samples, in 95 samples, the intercept or the alpha value will be varying between these two limits. But in 5 cases, it will be below this, either below this lower limit or above the upper limit. Doesn't matter. We are able to, we are suffering, we are allowing 5% error. Yesterday we saw that. Now, second is beta. Beta. The independent variable is advertisement. So beta coefficient is 9.58. See, 9.58 in the sample. 9.58 in the sample. Okay. So that means beta measures the influence of advertisement on sales. So the influence of advertisement on sales is when advertisement increases by 1 rupee, sales will increase by 9 rupees. 9.58 in the sample. What happens in the population? In the population, it will vary between 8.2 and 10.9. See here, lower limit 8.2, upper limit 10.9. In the population in 95 cases. In 5 cases, it will be beyond that. Is it applicable to the population? We have to look at the p-value here. See the p-value here. P-value is given as 2.71 E minus 0.8. 2.71 E minus 0.8. Now, this is a shortened way of writing the p-value. That means, you see that minus sign. When you have a minus sign here, see, there is a minus sign here. Minus 0.8. So, minus 8. Minus 8 means, E minus 8 means, this 2.71 value has to be rewritten as, this decimal point has to be shifted to the left side 8 places. This decimal point has to be shifted to the left side. Minus means left side. Plus means to the right side. So minus means this decimal point from here has to be shifted to the left 8 places. 1 place is already there. 2 is there. 7 zeros has to be added. 7 zeros has to be added. So the real number is here written here. 2.71 E minus 0.8. See, the decimal was here after 2. It is shifted to this place. 8 places to the left, including 2. So 7 zeros and 2. 8 places. So it's a long number. So the software is writing a short form, using a short form. The software is using a short form to write this. So the p-value is actually 0.000000271, which means the p-value is less than 0.05. Therefore, we say this result is beta value is applicable to the population. It is significant. I hope you have understood. Okay, let us move on. Multiple regression. Multiple regression means in the previous case we took only one independent variable. Usually there will be more than one independent variable. So if you take more than one independent variable, it is called multiple regression, used when there are two or more independent variables. The equation will be y is the dependent variable. There is only one dependent variable. Independent variable alpha plus, here I have shown two independent variables. First one is called x1. Second one is called x2. So beta for the first one is beta 1. Beta for the second one is beta 2. See? So x1 and x2 are the independent variables. Beta 1 and beta 2 are the respective coefficients. So in the result, what will happen? So here there will be intercept will be there. Supposing there are two independent variables, advertisement and parking space, for example. So there will be one here advertisement. Then below that there will be parking space. Then the values will be there. One more line will be added here. In the result, one more line will be there. Parking space, and the values will be given there. So that is what will happen in multiple regression. This is multiple regression. Okay. Now we are moving on to the second type of inferential statistics. Inferential statistics involve two types. First one is study of association between variables. Second one is analysis of differences between two groups, men and women, rural people and urban people. Is the difference in the values. So in correlation regression, the association between different variables in one sample is studied. We are taking one sample and we are studying the relation between different variables. Example, sales and advertisement expenditure in one company, one firm. Okay. In analysis of differences, the values of one variable is studied in different samples. Here we are studying only one variable, but in different samples are studied. For example, Advertisement expenditure in private sector and public sector firms. So we are studying only one variable, advertisement expenditure, in two samples, private sector firms, public sector firms. Is there a difference in the advertisement expenditure? We are studying the difference of one variable between two or more groups. We can use, say, advertisement expenditure in private sector, public sector, cooperative sector. So three samples, two or more samples. Here also, the basic question, are the differences in the values of a variable in the two or more samples significantly different? You are finding a difference in the sample. Is it significantly different, which means, is it applicable to the population? Is this difference applicable to the population? If it is applicable to the population, we say the difference is significant. Otherwise, we say the difference is insignificant. How do you find out whether the difference is significant? We look at p-value. If p-value is less than 0.05, we say the difference is significant. If p-value is more than 0.05, we say the difference is insignificant. So the p-value and 0.05 remains the same. Okay. The only thing is, what are the tests to be used for studying the analysis of differences? Let us look at the tests. There are three tests. Methods of analysis quantitative data. Z-test. Difference between two groups of large sample. Large sample means the sample sizes must be more than 30. When the sample size is more than 30, we say it is a large sample. If the two groups are having large sample, we use what is called Z-test. T-test is used again for difference between two groups, but the groups are small groups. The sample size is less than 30. Both the samples are having less than 30 size. Then we use T-test. Then F-test, ANOVA. Difference among more than two groups, whether it is small or big, doesn't matter. Difference among more than two groups, 3 groups, 4 groups, then we use ANOVA. So very clear, difference between two groups, difference between more than two groups. Now, in statistical textbooks, you will find Z-test and T-test, but we are using the calculations using software. So software, you don't have to say to conduct a Z-test or T-test to the software. Software will read the sample size and decide which test to apply. So because the software has all the formulas, the two formulas are different. So the computer software will read the sample size and apply the appropriate test. So now we only say, when in computer language, computer softwares, we only say T-test. We don't speak of Z-test. That is only in textbooks. Okay, T-test. If it is large sample, the Z-test formula will be applied. If it is small sample, the T-test formula will be applied. That's all. Software will do that. Okay, so we only have now T-test for difference between two groups, F-test for difference between more than two groups. Okay. So the basic logic is, what we do is we take the mean. We take the mean of the different samples. Supposing you have two samples, we take the mean of the first, mean value of the first sample, mean value of the second sample, and do the testing. The basic question, does the difference in the sample means reflect the difference in the population? Now we have understood that. Or we say, is the difference in the sample means significant? Same thing. One is English, the other is a technical way. Second one is a technical way of same thing, what we are saying in the first question. Z-test, T-test, F-test answer this basic question. So these tests are used to answer this basic question, whether the difference is significant. Now, types of Z-test and T-test. Now, we only have, in computer, we only have T-test. There are different types of T-test. Independent samples T-test. First type is independent samples T-test. For example, supposing in the class there are boys and girls, you are finding the marks, you are finding the difference between the mean marks of boys and the mean marks of girls. boys group is different from the girls group, though they are independent. So we say independent sample t-test. Paired sample t-test. Computer knowledge versus mobile application knowledge of the same group. So the group is same here. Group is same here, but we are testing two variables. Computer knowledge versus mobile application knowledge of the same group. So the pair. So one person will have two values, a pair of values. Computer knowledge value, mobile application knowledge value. So one person will have two values. So a pair of values will be there. So we call it a paired sample t-test. So two tests are there. Whether it is independent sample t-test or paired samples t-test, interpretation of the result is what you should know. Interpretation of the result is what you should know. The result will be given by the software. You should understand the result and interpret the result and find out and say ultimately whether the difference is significant. The software will calculate Z value or T value. We can also calculate it. There is a, if you refer to a statistic test, there is a formula. The formula is not very complicated. It is a simple formula. We can calculate the Z value or T value. We used to do that earlier. When you're studying the subject, you have to calculate the T value, Z value manually when you're studying statistics for in the class. So Z value or T value is computed and given by the software. Along with that, P value is given. We are interested in the P value. P value is also generated through the calculations. And this P value, as I said, indicates the probability of the difference between the means occurring by chance. So the P value should be less. If the P value is less than 0.05, the null hypothesis that there is no difference is rejected. We say there is significant difference. If P value is less than 0.05, we say that there is significant difference. That means there is difference in the population also. In 95% of the cases, there will be difference in the population. Only in 5 cases, there will be no difference. The difference is significant. It exists not only in the sample, but also in the population. If we take more and more samples, in 95 samples out of 100, this difference will be there. In 5 samples, it may not be there. It doesn't matter. So this is all very simple. Only interpretation is again very simple. Look at the p-value. If p-value is less than 0.05, we say the difference is significant. Okay, this is, now look at this. This is the software result. This is the result given by the software. Difference between two groups. Two groups. Hypothesis test. Look at the heading. Hypothesis test. Independent groups. T-test, pooled variance. Independent groups. Boys and girls. These are the marks, for example. Out of 100, the boys got a mean score of 46.55. The girls got a score of 44.09. The girls' score is less than the boys' score in the sample. Remember, in the sample. In the sample which you have taken, one sample. Standard deviation is calculated. This is a descriptive statistics. Mean and standard deviation are descriptive statistics. 14.41. Variation is more in the boys' score. Variation is less in the girls' score. Okay. N number of boys is 11. Number of girls is 11. It may be different. It need not be the same. Okay. The difference is given here. See here. Difference. Boys' score minus girls' score. Difference is 2.455. 2.455. See, there is difference. So in this sample, there is difference. Question is this difference applicable to the population? Is this difference applicable to the population, or is it applicable only to this sample? That is the question. For that, we look at the p-value here. See, t value is given here and p-value is given last line. P-value 0.6345. How much should the p-value be to say that this difference is significant or is applicable to the population? The p-value should be less than 0.05. Here the p-value is 0.6345. So we say this difference is not applicable to the population. It is not significant. It is only applicable to the sample. So we say in the population, there is no difference. This difference exists only in the sample. This is the meaning. This is the interpretation. So look at the result of the software, understand it, and you should be able to interpret it. This is very simple. Look at p-value, that's all. If p-value is less than 0.05, we say that the difference is significant. It is applicable to the population. In 95 samples out of 100 samples, it will be applicable. Now, ANOVA. ANOVA is used for more than three or more groups. Purpose is to test whether the samples are drawn from the same population or different population. Whether the samples are coming from the same population or they are coming from different populations. One-way ANOVA studies one variable in two or more samples. We are studying one variable in two or more: rural, urban, semi-urban, low income, middle income, high income. Okay. One example, capacity utilization is the variable that we are studying in public sector and cooperative sector. Okay. Two-way ANOVA studies one variable in two sets of samples. That is capacity utilization in public sector units of different age groups. So public sector units again subdivided into different age groups. That is called two-way ANOVA. But usually we study one-way ANOVA. We will look at one-way ANOVA. Interpretation. Result will be given. F ratio will be calculated. Is F test. ANOVA is called F test. F ratio is calculated. P-value is also generated. If p-value is less than 0.05, the null hypothesis is rejected. Null hypothesis means there is no difference between the two groups in the population. We are rejecting that and we are saying that there is significant difference in the population. Difference between groups is significant if p-value is less than 0.05. Okay, two-way ANOVA we are leaving out. Let us look at ANOVA. One-factor ANOVA. This is the result that you will get. How do you interpret? First of all, how do you understand? Then interpret. See, three salesmen are there. Three salesmen. Salesman 1, salesman 2, salesman 3. All of them are making sales. So in a month, their mean sales. The first salesman, 9 days or 9 months. 9 months sales. So N is 9 for the first salesman. His mean sales is 349.8. For the second salesman, again 9 months are there. His sales is only 336.4. Third salesman, his sales is 346. ANOVA table is here. We look at, so we have the values here. What we want to know is, in the sample, there is difference between salesman 1, salesman 2 and salesman C. There is difference in the sample for 9 months. We have taken the salesman sales for 9 months. If you take the salesman sales for all the months where he was working, that is population. Population is all the months that he has been working. That is population. N 9 months sample. So when you have studied 9 months, from this result we are going to understand whether these three salesmen, their sales are different when taking the entire their service. Okay. What we have to do is, so many things are given there. I am not going into that. We look at F value and P value. See here, F value, P value. P value is 0.2556. P value should be less than 0.05. Only then we can say that this difference which is there in the sample is applicable to the population. So here we say it is not applicable to the population. This is only applicable to this particular 9 months only. If you take the entire sales period, it is not applicable to them. Or if you take some other months, say some other 10 months or some other 12 months, it will not be applicable there. So this is applicable. It's a chance difference in this sample alone. That is the meaning, interpretation. So understand, interpret. Let's take another case. Sorry. 1 factor ANOVA, 1 factor ANOVA. Look at region 1, region 2, region 3. So the salesmen are working for, say, 10 months in region 1. Region 2, 10 months. Region 3, 10 months. So what is the mean? 345 for the first region. The average sales, mean sales for the second region for the 10-month period is 356. And for the third region, 312. So there's a lot of difference. 345, 356, 312. In the sample. The sample there is difference. Don't doubt about that. Question is it applicable to the population? If you take the entire sales of the whole so many years, will you find a difference in the sales of region 1, region 2, region 3? That is the question. Look at F value. See F value. P value. Look at P value. P value is given in the shortened form 4.76 E minus 0.5. Minus 5 means this decimal has to be shifted. See, this decimal has to be shifted 5 times here, 5 places here. 4 is already there, so 4 more zeros will be added. So 0.000, sorry. So this, now you know how to interpret this number. So the actual value will be 0.0000476. That means p-value is less than 0.05. So we say that this difference in the sample is also applicable to the population. When the difference is significant, applicable to the population, we do another test called post hoc analysis. Look here, post hoc analysis. That is pairwise analysis. Is there a difference between region 1 and 2, region 1 and 3, region 2 and 3? So pairwise, between which regions there is a difference. This overall difference is there. But now we want to know between which two regions the analysis, the sales is significant. See, p-values for pairwise t-test is given. See, p-values for pairwise means t-test is enough. 2 values. For 2 values, we use t-test. So, post hoc analysis, we are calculating the p-values for pairwise t-test. Say this is region 3. Look at region 3. Region 3 and region 3, of course, region 3 and region 1. See, region 3 and region 1, what is the p-value? 0.005. So, there is a difference between the sales of region 1 and region 3. That difference is significant also. Then region 3 and region 2. See, region 3, region 2, what is the p-value? P-value is 1.82 E minus 0.5. You know how to interpret it. So we have to shift the decimal places to 5 places this side. So 0.0000182. That means the p-value is less than 0.05. We say the difference between region 3 and region 2 is also significant. It is applicable to the population also. So this is how the result will come. You have to understand it, interpret it. Okay, now I'll just introduce to you what is called a parametric versus non-parametric tests. Parametric, 2 types of tests. Inferential statistics. There are 2 types of inferential statistics. Inferential statistics can be categorized as parametric and non-parametric. What we have seen so far, correlation, regression, t-test, ANOVA. These are parametric tests. Parametric tests are used when the population is normally distributed and the data are collected on an interval or ratio scale. So, these 2 types of tests are there. Which type should you use? That is a question faced by the researchers. Very often, even today, one researcher was asking me this question this morning. He sent a WhatsApp message and I replied to him. He was saying he was doing his research. Now he is confused about which test to apply. So very simple. We collect the data and we find out whether the data is normally distributed. If the population is normally distributed, the data that we collect from the sample will also be normally distributed. Normal distribution, I showed you a diagram, remember, bell-shaped curve. In the beginning, I showed you a bell-shaped curve. That's the normal distribution. So we collect the data from the sample, which represents the population, and we test the we test the normality of the data which we have collected. There are two tests. So applying those two tests, so again software will do that. Applying the two tests, we find out whether the data that we have collected, the data of the sample which represents the population, whether it is normally distributed. If you find that the data are normally distributed, you can use parametric tests. If the data are not normally distributed, you cannot use parametric tests. You have to use non-parametric tests. Non-parametric tests are used when these assumptions are not met. That is, this data are not normally distributed. So they are known as distribution-free methods. It can be used when the data are normally distributed, or so a non-parametric test can be used when the data are normally distributed as well as not normally distributed. Non-parametric tests can be used in both situations, but parametric tests can be used only when the data are normally distributed. So they are known as, this non-parametric tests are distribution-free methods. Mostly hypothesis testing situations have non-parametric alternative. We have seen t-test, we have seen ANOVA, we have seen correlation, regression. For each one, there is a corresponding non-parametric alternative is there, which can be used when the data are not normally distributed. So it is, in parametric test, we used mean, you would have seen that. For testing the difference, we used mean. In non-parametric test, we do not use mean, but we use the ranks of the observations and the median. We use the ranks and the median. Median means the middle one. So that is the difference. So parametric tests are using the means. Non-parametric tests are using ranks of the observations. Non-parametric tests can be used in both situations when the data are normally distributed as well as when the data are not normally distributed. But parametric tests can be used only when the data are normally distributed. Parametric tests are considered to be more accurate. Okay. Non-parametric test, the Mann-Whitney U-test. It is similar to independent group t-test. So when the data are not normally distributed, you want to find the difference between two groups, then we use Mann-Whitney U-test. It is the alternative for independent sample t-test. Wilcoxon signed rank test is the alternative to paired sample t-test. Paired sample t-test. The alternative is, the alternative non-parametric test is Wilcoxon signed rank test. Kruskal-Wallis test. That is the alternative for one-way ANOVA. Kruskal-Wallis test is the alternative for one-way ANOVA. Friedman test is the alternative for two-way ANOVA. Chi-square test is the test for independence of attributes, the correlation. Instead of correlation and regression, we use the chi-square test for independence. Dependence or relationship we are measured by correlation and regression in parametric test. Non-parametric alternative is chi-square test. Spearman's rank correlation is also used instead of correlation. Pearson's correlation is parametric test. Spearman's rank correlation is non-parametric test. Interpretation is the same p-value. Interpretation, look at the interpretation there. P-value indicates the probability of difference between the means occurring by chance. When p-value is less than 0.05, then a hypothesis is rejected. Interpretation again is same depending upon p-value. Chi-square test, I'll just explain the chi-square test also. Then I will stop. Chi-square test is applied in the study of Attributes. Chi-square test is commonly used. It's applied in the study of attributes like residential status, literacy. Is there a dependence between residential status of a person and his literacy? Are rural people less literate? Are urban people more literate, and so on? H0. Attributes are independent. There is no association between, there is no correlation, no association between residential status and literacy. Alternative hypothesis H1. Attributes are dependent. There is association. So we want to test this and find out whether that association, we want to test whether there is association in the sample, and also we want to test whether the association in the sample is applicable to the population. We prepare a two-way contingency table. A table will be prepared. I'll show you the table. Rows will be one classification will be shown in the row. The other classification will be shown in the column. Say gender may be shown in the row, and skill, literacy may be shown in the column. The software will calculate chi-square and p-value. So finally, it is p-value that we have to look at. P-value indicates the probability of the association between the attributes occurring by chance. If p-value is less than 0.05, null hypothesis is rejected. Same thing that what we have been saying. So this is, look at this, chi-square test. This is the outcome result which you will get from the software. See, urban people, so here in the row, urban people, semi-urban people, rural people. Columns, literate, semi-literate, illiterate. So 34 people, urban people out of 104 urban people. See, out of 104 urban people, 34 are literate, 47 semi-literate, 23 illiterate. Semi-urban, 115 people, 54 are literate, and 36 semi-literate, and so on. Rural people, 27 are literate out of 103. See the percentage, this is what we want. Out of 104, 34 means 32.47%, 47.0%, 26.2%. See here, there's a difference. The literate people, see, highest percentage is semi-urban people are having 47% literate. Urban people, 32. Rural people, only 26% are literate. So there is a difference. So urban people and semi-urban people are more literate. Rural people are less literate. So this difference is there in the population. So in other words, is there an association between their residential status and the literacy status? We are seeing a difference. So is there an association between that? Look at chi-square value. The value is here. We look at the p-value. 0.004. P-value is less than 0.05. Therefore, this two variables are related. There is an association. They are dependent, and it is applicable to the population. This dependence between the two variables are significant, or it is applicable to the population also. Okay, I think we'll stop here. These are the multivariate complex analysis econometrics. Okay. Softwares, there are different softwares, different types of softwares are there. Most common is SPSS. Other softwares are also available. Or you can do it in Excel, provided you download something called Megastat. It's an add-on to the Excel, which can be downloaded free. These are the textbooks for reference for this statistics. Elhan's book is very important. Good. Fundamentals of Statistics. Elhan's. Applying regression and correlation. If you want to study about regression correlation, the last book is very good. It's a small book, but it is very good. Fundamentals of Statistics by Elhan's covers all the different statistical tools. Levin's book also is comprehensive. Okay, thank you.